All right. All right. So, Unit 5 is when we started thinking about if I take a lot of samples, what's going to happen, okay? So, the definition of a sampling distribution is a distribution of an estimator if every possible sample is taken. Okay? And we focused on two types of estimators in this case. One of them is X bar, and one of them is P hat. And we call X bar and P hat unbiased because the mean of the X bars is the population mean. The mean of the P hats is the population proportion. In general, like if I take a sample and measure its mean, and we all take a different sample and measure its mean, we're all going to be really, really close to the mean of the population. And in fact, we would expect as many of our sample means to be above the population mean as below the population mean. Like they would balance each other out. Okay? And so one of the reasons this class focuses so much on the distribution of X bars and P hats is because X bar and P hat are unbiased estimators. An example of a biased estimator, S for sigma. And in fact, the whole reason we have to use T distributions is that S is a pretty crummy estimator of sigma. It's unpredictable and not quite that if we all take different samples and measure the standard deviations of our samples, they don't actually match the standard deviation of our population well. Okay? Now, when we talk about sampling variability in general, sampling variability is the fancy way of saying samples are not perfect. That while your sample is your best guess at what the population is, it is still not a great guess. It's still, so we would expect, again, if all of us take a different sample from the same population, we might all get a different sample mean, right? Our means would all be kind of close to each other, but they might not be perfect. In other words, our sample means vary, okay? What's weird about this is when we talk about sampling variability, like the X bar or a P hat are the variable. And mu / P are not a variable. Hi. Hello? Okay. There was no one there. Now I'm ready. I'll get it faster if they try again, right? Okay. Now, in statistics, remember, variable is something different because what's weird about this is when we take a sample, we know the answer to the variable. We don't know the values from the population. So the actual constant is the value from the population, but the variable is what we know. And in algebra, the variable is what we don't know, right? But it's always one number. Anyway. Okay. So, some rules. If I take every single possible sample and measure its p hat, so this would be, by the way, we use p hat to talk about categorical variables. If I was describing the hair color in this room, I would say 10% of the students in this room have blonde hair. But the variable itself, hair color, is categorical. We summarize it with a percentage, or a proportion, but the variable itself is a categorical variable, okay? All right, so the p hats are going to be normal if np and 1 minus p greater than or equal to 10. That is why the normal condition for p hats is np hat or np hat complement or np hat combined or np null, whatever it is, okay? The normal condition for the p hats for a z-test for p, the reason it's np and n1 minus p is that's what makes the p hats approximately normal, okay? The center of the p hats is p. The standard deviation of the p hats is the square root of p 1 minus p over n. In terms of your formula sheet, this part is on the formula sheet. Hello? No, I get it. I sent him to his mom. Yep. Bye. Are we good? Okay. If you're looking at the difference between two, so I have population A, I have population B. The shape of, so now this is p hat for P. This would be p hat A minus p hat B to estimate PA minus PB. Okay. For the shape, this one will be normal if NAPA, NA 1 minus P. And so essentially you're checking both. And the mean of those differences will be the difference between our two population values. I should probably write down the correct formula. And again, on your formula sheet. So, it is highly recommended that, we'll spend some time maybe thinking through that formula sheet. Knowing those standard deviations and stuff, so if I'm studying, I'm not studying these formulas, but I am studying the normal rules. Did you guys catch my drift there? Okay. All right. All right. All right. Now, This section is describing X bars. We would use X bars when what we're describing is a quantitative variable. And again, when you're trying to decide quantitative versus categorical, you're not looking at what we summarize with. You're saying, what would an individual response look like? And if the individual response is a word, it's categorical. And if it's a number, it's quantitative. So hair color is a word that's categorical. But if we said, what is the average height of people in the room, or we take it, you guys as a sample of Gravity Height students, we measure your height, the individual responses would become numerical values. Everybody good? Great. All right, so in this case, we're using X bar to conclude about mu. The X bars will be normal if one of two things. The easy one, my sample size is big. And we define big enough there as greater than or equal to 30. Now, when my sample size is greater than or equal to 30, I am not going to say that the sample will be normal, because it won't be. It's that if I took every possible sample, the means of those samples would be approximately normal. Do we understand the difference of what I just said? Okay? The sample, like let's say I have a super duper skewed right population. If I take a sample and it's a large sample, that large sample is not going to be normal. It's going to resemble my population. If my population's skewed right, my sample is going to be skewed right. Now, imagine every single one of us takes a big sample, all from the same population, that is skewed right. Lexi, what's your sample going to look like? Skewed right. What's yours going to look like? What's yours going to look like? If we're all sampling from the super big skewed right population, all of us are going to have a skewed right sample. Is everybody good? Now, what can we say about every single one of our population means, or our sample means? Yours is going to be really close to the population mean, and yours is going to be really close to the population mean, and yours is going to be really close to the population mean, and yours is going to, all of our sample means are going to be about the same. Everybody good? And so those means will be normal. Our samples, what are they going to be? Skewed right. Because our sample is going to resemble the population. But if we all had have similar samples, we're all going to have similar means. The means themselves would be normal. Everybody good? Okay. The other way my sample means will be normal if I have a small sample size is if I'm sampling from a population that is normal. And when we're checking conditions for like an inference procedure, the way we say, all right, my sample size is not greater than or equal to 30, is it reasonable to assume I'm sampling from a normal population? What do? We look at a graph of our sample and decide, is it reasonable it came from a pretty symmetric, well-behaved population? All right, now, we're just talking about two normal rules, yes? One of them is greater than or equal to 10. One of them is greater than or equal to 30. I swear I just thought of this. I've been teaching this class for 13 years, and I just thought of this to help you remember. If I draw a 10 bad, it kind of looks like a P. So proportions is a 10, is the one that's 10. If I draw a 30 bad, it kind of looks like a... The 3 of 30 could be construed as an M to go with means. Sure. Does that work?
Let's just go with the 10 one.
I think it's so bad that it might just stick.
A 3 looks like an M. A 3, well, like if I'm choosing between which one goes with P and which one goes with M, a 3 looks more like an M than a 10. Or something.
What if I draw my 3 so badly it looks like a 10?
Yeah.
Well, I literally, that would be bad. But Hayden, your handwriting is what inspired that, so. I was just playing. Yours is not even the worst in the class. Looking down, not accusing anybody of having the worst handwriting in the class. Still looking down. Hey guys, what is the mean of the X bar is going to be? What's
upside down 3.
mu? It's a rotated 3. It's technically 30 degrees in the clockwise, counterclockwise rotation. 90 degrees in the clockwise.
Yeah, translation.
Something like that.
Rotation.
Does anybody remember the standard deviation of the X bars? Don't worry, you don't need to remember it. It's on your formula sheet. The poster's gone after probably today. Don't rely on the posters. They're gone. Like, I could just slowly take them down as we go. Huh?
That was the last week.
You guys think I can make it from here?
Absolutely not.
Use less than 0.5.
Although I feel like the bigger it's gonna fly better.
Yeah, but when you're as bad at doing this as I am,
Be the test. Does it matter?
like, it's just going to fly better in the wrong direction. Just so we're clear, I'm aiming for the recycle bin, not the trash can.
Oh, okay. You have a backboard.
Ooh. This is cool.
That was way better than I thought it would go.
Not bad.
Way better than I thought it would go. That was actually close. Okay, so, all right, now let's talk about X bar. I'm using X bar A minus X bar B to make conclusions for mu A minus mu B. Essentially, you are checking the normal condition for both samples. Okay, so you would only have 2 sample means if you have, 2 samples to take the means up. I've never in my life seen a question where what they do is the sample size of one is greater than 30 and then the other one's coming from a normal population. Technically, that would work. You're basically checking these conditions for each sample. Okay? And as long as one of the 2 are met, you're good. Someone's going to have to help me with that one eventually. Because I'm not going to be able to reach it. I don't even know if sitting on a chair gets me there. We'll see. All right. The mean of X bar A minus X bar B is mu A minus mu B. And again, these formulas you don't have to memorize. You have to be able to use. Now, you guys, when I say the distribution of X bar A minus X bar B, when we talk about X bar A minus X bar B, how many numbers is that? Like I draw a picture, and the distribution, this is the distribution of X bar A minus X bar B. And let's go ahead and say that I know mu A equals 21 and mu B equals 18. This center is 3, and I talk about this one point right here. That point represents one number comprised of the means of 2 samples being subtracted. Okay? So it's really easy to look at this symbol and think that means 2 numbers. It is not 2 numbers. It is one number based off of the difference between 2 samples. So we got to be really careful about that, okay? The average time it takes for a towel to air dry on a sunny day is 102 minutes with a standard deviation of 15. You set 7 towels on the rack to dry. What is the probability that the mean drying time of 7 towels is less than 90 minutes? Oof. So as I read that question, okay, the first thing that jumps out at me is I want to find the probability of something being less than 90, but what symbol would I use for that something? Because that is asking the probability that X bar is less than 90. Is everybody good so far? All right. So if that's the case, I would need to think through, well, what is the mean of my X bars? What is the standard deviation of my X bars? What is the shape of my X bars? What is the mean of my X bars? Which is? 102.7. My standard deviation is no. That is my standard deviation of individual towels. My standard deviation of the X bars is 15.3 divided by the square root of 7. I don't know what that is. But I got something that does. What about the shape of my X bars? Huh? Yeah. In the, we weren't told anything about the population. Now, that being said, y'all, do you believe, on what you know about normal distributions, that this population would probably be normal? I think so. Assuming all the towels had the same level of, are they dripping wet? Are they, as long as they have the same level of that, I think the same amount of water currently hanging in that towel, right? I think it's fair to say normal. So I'm going to say must assume, but I do believe it is reasonable that the population is approximately normal in this case. So the big trick of this is recognizing, essentially, that if I'm asking you to find the probability that the mean is something, you need to use the standard deviation of the means. And then less than 90 would be over here. And then what would we do in the calculator to find that? Normal CDF. Negative a gajillion to 102 points to 90. Now, let's say instead I gave you something kind of like this. Let's say I gave you these hypotheses for a significance test with this as my mean. And this, again, assuming conditions are met. And I get this is 0.014. What is the name of that calculation? That is your p-value. It is what what's going on here? This is if these are my hypotheses, this is the null hypothesis is true, and the probability we could see the observed sample or more extreme. And in this particular case, this would give me like pretty good evidence that the mean time it takes for these towels to dry is smaller than 102 minutes or 103 minutes. Every good? All right. Let's jump over to Unit 6.